So here's a brief video about how to work with Jamovi. After you've opened the program, it should look like this one. So we need to open the data. Therefore, we can click on this little button and then we click on Open. Usually you should have a statistic folder where you have all your files. Yeah. I have my file that I want to open now in the download folder. And I want to open, in this case, where is it? So many data sets. Here I want to open the data set first survey. So I open it. Now I have the data in Jamovi. You see, he automatically recognizes the headings of my variables. And if you look on the variables themselves, here you find all the variables. This is an option where you can work on your variables. For example, you can change, let's change study satisfaction. Yeah, here you see study satisfaction was a scale from 1 to 10. So that is not nominal, but interval scale data. I don't know exactly why now the values vanish here, but however, now we have put it on interval scale data. It's called here kontinuierlich. So let's click back. The important procedures, especially for the exams, you find under Analyze. And let's start with data exploration. After that, we will have a look at t-tests at the ANOVA. Here you find the correlation analysis, and here you find the chi-square independence test for cross tables. So let's start with data exploration and the descriptive statistics. So here, for example, you can show certain values. We have here one interval scaled variable. Let's put the variable into this window. Now Jamovi automatically calculates the average, the median, the standard deviation, minimum and maximum. If you want to have additional key figures, you can here open this menu of statistics. And there, for example, you can say, okay, I also want to have the mode. Yeah. Or you can say, I also want to have the variance. Then you see the mode and the variance added here. Or you can take out the minimum and maximum because they are not important for you for what reasons ever. What you can also do, you can add some diagrams. You have to look out here a little bit. That is one of the weaknesses of Jamovi. For example, for interval scale data, you cannot create a bar chart. You would need to create a histogram. Yeah, and then you have also a chart for the data here. So you also could create a box plot. Yeah. Box plot basically means that you have here on the y-axis the scale. You have values between 4 and 9. And then you have 25% in this area between 6 and 4. You have within the box, you have 50% of the values. So 50% of the values between, that is 7.5 and 6. Here's the median is at 7. Yeah, and then you have 25% at the whisker above. So between 7.5 and 8. Okay, so for some reasons we can also not create a frequency table for interval scaled data. What is a pity? Yeah, you can use a trick. For example, you can go back to the variables and put your data, edit it, put it back on nominal, and then go back on data exploration, descriptive statistics, and now you can take the variable satisfaction with studies. Now we still calculate the average, but now you can also create a frequency table. I don't know why he don't create frequency tables for interval scale data. I don't know, but that's just the case. Okay, so that is the first point that we have talked about, how to calculate certain key figures. Key figures like the mean, the median, the mode, the minimum, maximum, standard deviation, variance, and so on. There are even more key figures like the kurtosis, the standard error, and so on, confidence intervals, but that is more for statistic too. So we also talked about how to create frequency tables, and we can also this frequency table now we can show it with a bar chart, yeah, because we have changed the data type. But the most important thing what we need to do on Jamovi is we want to do our statistical tests. Basically, we have to deal with three different tests. First, the chi-square test. The chi-square test we usually use to evaluate differences in cross tables, and to what we basically do is we calculate a p-value, and the p-value always gives you the probability that the null hypothesis is true. The null hypothesis is usually there is no difference between two groups, or there is no relationship between two variables. Our research hypothesis, that we also call the alternative hypothesis, would be there is a difference between two groups, for example, males and females, or there is a relationship between two variables. We always apply the chi-square test to evaluate differences in cross tables. What we also need is the t-test and the ANOVA. We always apply the t-test and the ANOVA when we compare means of groups. If we compare the means of two groups, then we use the t-test. If we compare the means of more than two groups, then we use the ANOVA. And then there is a different t-test that we also apply when we conduct a correlation analysis. So let's have a look at these tests. So first we want to apply the t-test. If you click on t-test, you see there are different t-tests, but for us important now is the t-test for independent samples. Independent samples means that we split our sample into two different groups that we want to compare. For example, again, men and women. Yeah, so let's evaluate the hypothesis that men and women are different on the left-right spectrum. So we click on t-test, we take the left-right spectrum, which is about political attitudes, in the dependent variable, and we put gender into the grouping variable. And it's a little bit counterintuitive. Usually what we do, we first measure, do we have any differences in our sample? And then we calculate the p-value to calculate how likely is it that the difference in our sample is just a coincidence, and that in the whole population there is no difference. How likely is it to measure a certain difference even if there is no difference in the whole sample? Yeah. So first we need to measure. So if you click here on descriptive statistics, then you see the results. So you see here females are more on the left side with a value of 3.26. Males are more on the more to the center, 4.2. 6. Now the question is this difference significant? And significant in this case does not mean that it's big or small. It does mean, uh, how likely is it that this difference also exists in the whole population. Therefore, we calculate a p-value that measures how likely it is that there is no difference in the whole population. The p-value is here 0.027. That means 2.7%. Yeah, and that is enough evidence then to refute the null hypothesis. So the difference that we have measured is significant. That means we assume that this difference also exists in the whole population. This cannot be a coincidence because that is very unlikely. Therefore, we consider our alternative hypothesis, which is also our research hypothesis, that there is a difference between men and women according to the political attitudes, as being proven. Yeah, because a p-value is smaller than 0.05. So in the exam or in a research report, you would have to write a sentence like, we have observed in our sample a difference between men and women in their political attitudes. Women are at 3.26, men are at 4.26. The p-value is 0.027. Therefore, this difference is significant, and we can consider our alternative or our research hypothesis to be proven. Maybe it makes sense to pause the video now for a moment and to try to evaluate other hypotheses that you would evaluate with the t-test for independent sample. For example, there is a difference in how satisfied people are with life between working students and not working students. Yeah, we have two groups: working students and not working students. Satisfied with life is interval scaled, so you can compare the means. We will continue with the next procedure. The next procedure is a procedure that we apply when we have more than two groups. And in this data set, we have, for example, our variable class. We have 5 different classes. And what we want to do is we want to compare the study satisfaction of these different classes. So we have more than two groups, therefore we apply the ANOVA, but we want more than two groups, but we want to compare averages, so that is where the ANOVA is for. And we will only work with the 1 factorial ANOVA so far. So click on 1 factorial for ANOVA. ANOVA is a shortcut, by the way, a shortcut for analysis of variance. So we take the class as a grouping variable, and the study satisfaction is a dependent variable. We think it depends on at which university or in which class you are. Again, we have the test here and we have a p-value. We already see that the differences are not significant. We have a value of 0.448 or 44.8%. That the null hypothesis is true, and the null hypothesis always is there is no difference between the groups. But therefore, still we want to measure, we want to have a look at the table with the descriptive statistics. Yeah, and here you see we have measured some differences between the classes, not so big, but the number of students in these classes are also very small. So there's one rule. Obviously, the sample size has a big influence on the p-value. And if you have small sample sizes, then even if you measure more or less big differences, they will not be significant. Yeah, small samples are not good proof for your research hypothesis. But if you have a big sample size, then you have another problem. Then even sometimes differences which are very small and not very important are significant. Okay, so I would again propose that you pause the video for some minutes and to evaluate other hypotheses. For example, the hypothesis that the life satisfaction is different per class. Yeah, life satisfaction, again, interval scaled, uh, class more than two groups, so therefore you would also apply an ANOVA. or the alcohol consumption is different between different classes, or the left-right spectrum is different between different classes, and so on. So there are tons of variables that you can evaluate here to practice the ANOVA. So next procedure we want to look at is the chi-square test. As I said, the chi-square test you need to evaluate differences in cross tables to see if the differences that you observe in your sample are significant. So you find the chi-square test here among frequencies. Here is a chi-square test for independent samples. So for a cross table, usually you apply a cross table when you have nominal scale data. So here, for example, you can say the class is nominal scaled and gender. So your hypothesis would be that the percentage of men and women is different in different classes. That would be your research hypothesis. Your null hypothesis would be the opposite. The percentage of male and females in the different classes is the same. So you put class into the rows, gender into the columns. Then here automatically your cross table will be created, and you see that you have 15 females in the class of the public university, but you see you also have there 28 students from that class, so much bigger the class. So it's difficult to compare these numbers. Therefore, it makes sense to have a look at the percentages. And if you click on cells, there you find the percentages here. And let's say one class should be 100%, so the row should be 100%, and then we want to see how many percentage are female and how many percentage are male. So it's percentage in the row, and you can delete the observed value because you see the cross table now is a little bit confusing, so you don't want to present confusing data. So now you can see that indeed in fashion management, for example, you have 100% of females. In media management, here 60% of females, and so on. Now you can better compare the classes. But what you see here in the p-value is, again, it's higher than 0.05, so 5.4% basically. So therefore, you would say you have not enough evidence to prove your research hypothesis. You cannot prove that the percentage of men and women in the different classes is different. But that has to do with a small sample. If you would have a bigger sample, then you would already be able to prove it. Let's briefly have a look at all the other options that you have here. Under statistics, for example, you find a lot of different values. We will not go through them now, but you see the chi-square, which is a p-value here, is already marked, so it is calculated. If you also want, for example, calculate phi and Kramers V, these are numbers for how strong the relationship is. You can do that by just clicking on it. Yeah, let's also have a look here at diagrams. Here you can create a bar chart. You see you have the different classes. The blue bar are the females. The yellow bar are the males. You can change the form, use a stapled form of bars. Yeah, you could also use the percentages in the row, so it would look like this one. Then it's easier to compare the percentages. Okay, so this is the chi-square test. Again, I would propose that you make a pause. Now, for example, you could evaluate if the percentage of working students is different in different classes, or you could even evaluate if the number of correct answers for the question about the population is different in different classes. So the last one is a correlation coefficient. Correlation coefficient shows if two variables correlate with each other. For example, you would assume that the IQ and the results in the statistics exam in some way correlate with each other. So, or the time spent preparing the exam will strongly correlate with the result of the exam. So this would be both measured as interval scale data, and therefore you would be able to apply the correlation coefficient. In our case, for example, let's evaluate if there is a correlation between how satisfied students are with their life and how many alcohol they drink. So the question would be, are students who drink alcohol more happier or less happier than students who don't drink alcohol? Our null hypothesis would all again be there is no relationship. Our research hypothesis would be there is a relationship. You find the correlation analysis here under regression, because that's basically, yeah, there's some relationships to regression. And here correlation matrix. Yeah, so let's click on correlation matrix. Now all you have to do is you have to put the two variables that you want to evaluate, so study satisfaction and alcohol, into this field, and then automatically basically everything is done. Yeah, what you see here, here's a correlation coefficient is calculated at 0.119. And the p-value is also calculated. The p-value is easy to interpret again. It's higher than 5%. Therefore, we cannot refute the null hypothesis. So we cannot prove that there is a relationship between study satisfaction and alcohol consumption. Nonetheless, we measure that there is a small relationship, 0.119, and therefore you need to have some information how to interpret the correlation coefficient. The correlation coefficient always is between -1 and +1. -1 would be a perfect negative correlation. That means the more alcohol you drink, the less you are satisfied with your studies. +1 would be a perfect positive correlation. That would mean the more alcohol you drink, the happier you are. And then you can interpret the values between 0 and 0.3 is a small correlation, between 0.3, 0.6 is a middle correlation, and if it's higher than 0.6, so between 0.6 and 1, that would already be a high correlation. So here we have 2 times interval scale data, but you can also apply correlation analysis to ordinal scale data. You remember ordinal scale means that you can rank order the values, but the difference between the values is not the same. So for example, typical example for ordinal scale data would be the educational degree, or also if you have grouped data for income, for example, 0 to 1,000 euro, 1,000 to 2,000 euro, and so on. But if you apply the correlation coefficient for ordinal scale data, you have to apply a different correlation coefficient. This is, as you see here, Pearson's correlation coefficient. For ordinal scale data, you need to apply Spearman's correlation coefficient. It is calculated a little bit different, yeah, but you see the value here for Spearman's rho, 0.13, is not such a big difference to Pearson. So again, I would propose that you calculate some correlation coefficient and also try to understand how to interpret the results. Do we have a correlation, a strong or a weak correlation? For example, you can calculate a correlation between left, right, and satisfied with life. Yeah, the null hypothesis would be there is no relationship between the political attitudes and how satisfied someone is with his life. The null hypothesis could, for example, be there is a difference, or could also be a directed hypothesis like left people or right people are happier with their lives than people in the middle, something like that. You can also calculate is there a relationship between how someone rates his general knowledge and how happy he is with life. Yeah, so people who know more, or at least who think that they know more, are happier in life than people who think that they don't know so much. You can also use a variable like being reserved. would you describe yourself as a reserved person? Are reserved person happier in life than people who are very outgoing? And I would expect that people who are outgoing are a little bit happier in life. But these are just hypotheses that you can evaluate with a correlation coefficient of person because they are all interval scaled. So practice that a little bit so that you get used also to this procedure. So this is it basically. Yeah, we started with data exploration, descriptive statistics, where we basically evaluate just one variable. And then we continued with hypothesis testing, where we evaluated the relation between two or more variables. So the t-test we apply for independent samples when we split our sample into two groups and we compare the means. The ANOVA we apply when we compare the means, but we have more than two groups. The correlation analysis we apply when we have 2 times interval or ordinal scale data and we have then different correlation coefficient, persons or Sperman that we need to calculate. And the interpretation of the correlation coefficient is it is always between -1 and +1, and values between 0 and 0.3 are weak correlation, between 0.3 0.6 a middle correlation, and higher than 0.6 would be a strong correlation. And we have created cross tables and tested the differences in cross tables for significance with the chi-square test, yeah, that we need to apply when we, for example, evaluate the relationship between 2 times nominal or nominal and ordinal scaled variables. Okay, I hope that video was helpful. Yeah, ciao.